to that. Now, keep in mind, the seeing could have been awful. I have no idea, you know. But in terms of the precipitable water vapor, it was very nice. Obviously, these are not such good nights here. You probably want to do optical spectroscopy. I don't know. Here's some additional data. This shows you the percentage of nights during each of these months in 2001, which the water vapor was below 2 millimeters. And so this is probably a more important slide. So if you take March and December of that year, roughly a third of the nights, even April, roughly a third of the nights had precipitable water vapor below 2 millimeters. That's really, really good. Those would have been extremely useful nights. The average is about 11% of the nights across that year, roughly 11%. That's not bad. So what this is basically telling us that it appears that the data supports the conclusion that the site is a reasonable mid-IR site. Okay. This is the one I was thinking of, Enrique Perez. I don't know if he ever told me I could show this to anybody, but I'm going to show it to you anyway. I guess it's radiosonde data. And this is interesting because this couples more this site into the experiences that I've had at other sites. And what you can actually see here, this shows you, the two plots are the same. This plot is just this region here, blown up a little bit. You're looking at the percentage of time in which the water vapor is below the value shown here. Okay, so in other words, if we take a look here, just come on over here, if we say that we'd like to operate generally at under 3 millimeters of water vapor, then what it tells us, this is La Palma, ORM, this is Mauna Kea, which is really extremely good, of course. Then you see that roughly roughly 25 to 30% of the nights have a precipitable water vapor below 3 millimeters. That's pretty good on La Palma. On Mauna Kea, it's pushing 50%. It's not nearly as good as Mauna Kea, but still quite acceptable. And I think that's the conclusion you should come away with. 2 millimeters, you know, Mauna Kea is a factor of 2 better, but we're still getting 10 to 15%. So these are pretty consistent with the other data. So the overall conclusion, then, is that it is a pretty reasonable site. Not the greatest site, but it's a reasonable site. Yeah, Chris? Sure. Yeah. Did Maria Rosa, was she part of it? I don't know where Maria Rosa is. Was she part of this? Yeah, okay, right. Okay. All right. I'm sure there's more data. This is all that I've seen. This is the only data. These and Enrique Perez's data. Okay, so the conclusion is it's probably pretty good. Now, let me just say the following really kind of quickly, and that is, obviously, you need to monitor the water vapor in order to know whether you've got a good night where it's worth setting up and getting started in the mid-infrared. Traditionally, in the past, what we've done is we did this with T-Rex, with instruments, our other instrument, Oscar, is you can self-calibrate the system, as it were, by taking 2 standard filters, a 10-micron filter, usually broadband N filter, as well as a 20-micron filter, some fiducial filter. And then you begin to set up a database. You begin to accumulate a database. You look at standard stars. You get the raw numbers on the star through the 10-micron filter, the raw numbers through the 20-micron filter. And then you can go on and begin to do work that night. And what you will find is that there's a very clear correlation between that 10 to 20 micron ratio, because on bad nights the 20 micron goes down, and your ability to do work at 20 microns. And so, and over time, you will put this database, and you will have associated with it remarks about how easy it was to observe on those nights and get data. So in the longer term, you will be able to accumulate a database that allows you, at the beginning of a night, to actually determine whether that is a decent night to observe at 10 and 20 microns in the mid-infrared. Now, ideally, of course, you don't want to have to take a long time to accumulate that database. You'd like to be able to calibrate this ratio fairly early on with some kind of water vapor monitor. On places like Mauna Kea, of course, there are water vapor monitors up there that allow a pretty rapid calibration of that ratio and its quality, and the quality of the night that it corresponds to. So I don't quite know what to expect at ORM with respect to monitoring, but one way or the other, we will set up this kind of a ratio, and we'll be able to tell fairly early or throughout a night whether the night is good, a medium, or lousy, and somebody should do something else. Chris? And especially in the Q mode, where you want to switch, if it's not a really good night, just switch to another instrument. So, yes, yeah. Oh. Eduardo. It's not clear that there's any straightforward connection with the sea. So you could have a night in which the seeing is lousy, but you have just incredibly good transparency. It's just, there's no simple correlation with the seeing, as far as I know. In the country, are you saying? Yeah, you can have good seeing and high water vapor. Sure. Yeah, they depend to some extent. I guess they're decoupled. You know, the upper atmosphere is fairly complicated, but there are also issues, of course, about. I mean, the water vapor can arise at different levels, and the seeing is affected obviously by what's going on at different levels, and they can actually be decoupled. You mean a night in which the seeing is bad? Sure. One of the possibilities would be that you want to work at 10 microns and not at 20. So at 10 microns, we're far more impervious to the water vapor. And there are a lot of nights when you can work at 10 in the 10 micron band, but not at 20 microns. I'll say a little bit more about that. And that's not infrequent. And so, unfortunately, a lot of times people come in with a 10 and 20 micron program, and then say it's always good to have a backup program that just focuses on the 10 micron in case you're out of luck with respect to the water vapor. So, yeah.
One, you should remark that provided we have reasonable seeing, you will be diffraction limited.
Sure, I'll cover that point.
And I would like to make a remark also. If you want to ask questions with the microphone, because otherwise the people listening to the streaming system will not hear the question.
I mean, you touched on an important feature of telescopes, and that is Q scheduling. I mean, you wouldn't perhaps expect it to be available in the early days of a major new telescope, but presumably the intention will be to have Q scheduling at some point, so that you can optimize observations to the conditions, which is particularly important for the mid-IR, as you pointed out.
Sure. I think that the long-term intent is to have Q schedule, have CanariCam coupled into the Q scheduling process. Now, there are currently some limitations that are inherent, because when the contract was signed to develop CanariCam, the software system of the GTC was still somewhat in flux. And as a result of that, and I'm sure Marisa remembers quite well, as a result of that, it was decided that the best approach was to have CanariCam be a fairly standalone system from a software control standpoint. And what that means, though, that was fine, and the software is developed and it's fine. But it does mean that it's less integrated into the control system of the observatory than is optimal for Q scheduling. And so OSIRIS, for example, is nicely coupled into the system and is what we call compliant. So one of the follow-up activities that we are hoping to initiate sometime very soon is to make CanariCam compliant so that it can more easily fit into the Q scheduling operational model. Now, I have to say, I don't think, personally, this is my personal opinion, that even given the current software configuration in terms of control, that CanariCam, given the current configuration, I think it should still be able, one should still be able to fit it into the Q model, but it'll just be somewhat more complicated to do that. And I think once we get used to operating this way, we'll be able to figure out how to do that until we can make the system fully compliant. Because there are some other advantages to full compliance, one of which is the phase 2 of the proposals. And that'll make a big difference. So, nevertheless, Q scheduling, we're going to want to do it for sure, because you know, if you have a great 10 micron night, you're going to want to be able to bring the instrument in, and vice versa. Okay.
I have also a very short question.
Yeah.
Can you give me an idea where the corresponding curve for the Paranal or Lassie observatory?
I don't have those curves for you. I'm sorry.
It's closer to maybe it's closer to La Palma one, or?
I would say I think probably they are more similar to Cerro Pachón, and Cerro Pachón is clearly, which I have some familiarity with. Just I don't have the numbers, but Cerro Pachón is I suspect somewhere roughly, maybe it's more like Sierra Nevada shown there, and so I'm guessing that La Silla, I don't know, but anecdotally, La Silla is probably similar, and the Paranal are probably similar to Pachón, maybe a little bit better, not as good as Mauna Kea, and so. So this curve probably tells you a little bit more about what the VLT is up against. Of course, they have other issues, the seeing and issues that come about. Okay, I won't say too much. I'm not very knowledgeable right now about the performance of the mid-IR instruments on Lucia that we were talking about a little bit earlier, but there's going to be an upgrade to an instrument, and so to Vizier, but that's a different story. So. Okay, let me proceed. Other things, let's talk a little bit more about the infrared background. So this shows you the emission at Mauna Kea. So this is actually the number of photons per second due to the background. This is due to the atmosphere. Here's 10 microns. And what you see is right here, this is the, right here. This is the near infrared down here. This is the 10 micron window. Obviously, it emits less and it absorbs less. And so here's the atmospheric window here, and then here's the 20 micron window here. And you can see how much more background is in this region as well. This curve corresponds to a 2% emissive telescope. Of course, the telescope emits. And so this is probably a pretty good Mauna Kea night. And you can see actually that in the 10 micron region, the main background that you might see easily. Most telescopes aren't as good as 2%. That's pretty good. I think that the target for the GTC is it 5%? 4 or 5%. The Gemini South telescope achieves 3%. But you can see that if we have 5%, this curve goes up. It's just proportional, so it's going to be up around in here. So in the 10 micron region, it's not going to be the emission from the atmosphere that dominates the background, but it's going to be the emission from the telescope. So keeping the telescope clean, keeping the emissivity down is extremely important. That's no problem in the 10 micron region because the atmosphere dominates. Now, just so you know, there are two issues about the background from the atmosphere that are important. One of which is that obviously if the atmospheric background dominates, then slow fluctuations in the background level will contribute to the noise. And chopping and nodding help us get rid of that. We'll talk about that in a second. But the ultimate, even if that were not a problem, the fundamental noise is the shot noise, the particulate noise, the photon noise that arises in the photon stream from that background. So ultimately, you can't do any better than the photon noise in the background. So when you do the signal-to-noise ratio calculation, we'll talk about that shortly, the signal is your astronomical signal. The noise is actually the square root of n Poisson or shot noise associated with the background emission, hopefully from the atmosphere, but the telescope, if the telescope emissivity is too high. So it's the square root of n. That's your noise. So you've got this emission from the atmosphere. And let's assume, well, and emission from the telescope. So we use this technique to, what we want to do is we want to essentially get rid of that average background flux from the sky and the telescope. Now, again, you can't get rid of the shot noise. That's your fundamental noise. So what we do is we use a technique called chopping and knotting. And I hope I don't get too tied up trying to explain this. I hope that the plot is fairly self-explanatory. So you have your secondary mirror of the telescope oscillates at a few hertz. And it oscillates such that this is your array field of view, let's say. And so in one position of the secondary, you'll have your target, say, centered on the array. And in the other slightly tilted position, you're looking off to the side, so at some other region centered, just a little adjacent region centered on the array. Okay, so now what you do is you nod the telescope and to reverse the positions of the star, so that when you go to the other chop position, the star is centered or the target is centered, and now in the other chop, as you're oscillating, the other chop position of the secondary mirror is off to the side. Okay. And what the chopping actually allows you to do, it removes the average amount of sky noise because you subtract this image from this image. And that gets rid of the average background. And of course, at this location, you've moved the target, so the target isn't there, so you still got your target flux. You haven't subtracted that out. So you remove the sky background emission, as long as it's not varying too quickly. It can't be varying faster than a few hertz, but clearly it doesn't remove the shot noise. I keep repeating that because sometimes it takes a long time to convince my students that you can't get rid of the shot noise. And it does remove lower frequency detector noise, which people don't appreciate. So that's an important reason for chopping fast. The detector is noisy. And ultimately, you can't tell the difference between the detector noise and the sky noise. Okay. You nod, so that's why you chop. Now you nod over to the other telescope position, because when you subtract this from this, there's a residual. You've changed the collimation of the telescope, and there's an imbalance in the emission as viewed at the detector of the thermal configuration of the telescope. And there's something left over. So you subtract these, but there's still excess emission from the telescope due to the imbalance of the observing. These are not very well collimated. This was in the early days of Gemini. I can't even remember what. But you can see there's a negative image and a positive image because you're subtracting one from the other. And then you combine these two in order to get rid of the emission from the telescope, which is called radiative offset. The nodding, which is the motion of the telescope, occurs every 40 to 60 seconds. The chopping occurs pretty much continuously at a few hertz. Nodding is also called beam switching. And this allows us to permit the removal of that telescope emission. The separation between these beams we call the chopper throw. These are some real observations made with our Oscar instrument ages and ages ago. And this just shows you, to put some meat on these bones, this just shows you an image. You can see how bad the image looks. There are all kinds of detector artifacts. On source, off source, off source, on source. Then you nod. This is the nod position B, nod position A. You take the difference, you get this, and you can see that this image looks like this image, except this is the negative of this one because you've subtracted the on source from the off source here and the off source from the on source here. If you subtract, or if you take essentially the difference between these, you get rid of the imbalanced thermal emission from the telescope, and you get an actual image of your astronomical source without all of the background in it. This may sound pretty complicated. It isn't, and I'd be happy to go into it in detail offline with anybody who wants a more detailed consideration. Let me just say one more thing about the background. The background can be easily 500,000 times brighter than the object you're trying to detect. 500,000 times. Think about that. So this technique, while it's a pain and it drives an important component of the telescope, which is the chopper, you're getting rid of background which is 100, 200, 300,000 times brighter than your astronomical source. And it really works. It's a remarkable technique. Okay. You obviously have to worry about things like having a chopper throw, which is a separation between the two beams, which is smaller than your source size, because then you're actually chopping out your source. So these are all issues that, you need to think about. Okay, just a quick comment about definitions, because this is a source of endless confusion. We usually call on-source time, that's the amount of time that the source is actually centered in the field of view when you're chopping. So the chop time is the summation of when it's on source and when the source is off to the side. And the total time is this plus overhead. So usually this is the clock time. But in fact, different observatories have different definitions, and different manuals use different definitions. So I strongly urge you, when you're writing a proposal, be very, very careful about the times and the definitions, and don't take them at face value. You need to look into it. Otherwise, you'll get completely messed up. Okay, so you should, if in doubt, ask. An incredible resource for you to look at a lot of these issues is the Gemini website. They have a mid-IR resources webpage. We've helped with many aspects of this. Our students from Florida, who are now on the staffs of these different observatories, put much of this in place. And so I highly recommend it. It describes the procedures, calibration, data reduction, and so on. So it's a really useful site. Okay. Okay, something about the mid-IR, and that is the profiles. This goes back to a comment that Jose Miguel made. Keck is obviously a pretty good example of a telescope like the GTC. The profile that you get, the point spread function, look, this is an actual point spread function from the Keck in the mid-IR. And you can see, first of all, it's fairly complicated. Remarkably, it looks like a hexagon. Gosh. And you can see these kind of weird spikes and so on. And this is a model that Chris had put together from an optical analysis program. And you can see that this looks kind of like what you expect it to look like. And this is what the profiles in the GTC will look like. In the mid-infrared, the diffraction disk is quite a bit larger. Obviously, it's proportional to wavelength. Lambda over D is roughly a 0.2 arc seconds at 10 microns. The nice thing about that is, the bad thing is it's bigger than in the optical and in the near-infrared. But the nice thing is that because the seeing is substantially less, the seeing disk is substantially less in the mid-IR than in the optical, it turns out that most of the time we're very close to being diffraction limited at 10 microns. What that means is that, of course, you can plan pretty nicely to be close to the diffraction limit and make your put your programs together under that assumption. But it also means that, of course, we're very sensitive to the optical performance of the telescope. We can see, before anybody else just about, we can see the aberrations and misalignment, lack of collimation, and it all shows up in the mid-IR. So this is actually a pretty valuable diagnostic tool for, especially in the initial phases of telescope operation. Okay. I don't want to bog you down with you know, I guess you call them more arcane comments about CanariCam. Nevertheless, let me just give you a quick summary of the design. The instrument, this is a cartoon of the instrument shown at the Naismith A station, or one of the Naismith stations. I guess at this point it didn't matter. There's the camera doer here, the electronics racks, and you can see the frame to which these guys attach. Here's our engineer, and this shows the interface plate, which you see right there, give you some size of this whole assembly. And here's the, I think this is probably Naismith B. I don't think it's Naismith A. And there's the A and G. Those are the A and G arms. The plate that you see right here, those holes, I believe, attached to those holes, if I'm not mistaken. And so, again, it gives you some idea of the scale, and now you can see how big the instrument complex will be compared to some individuals there. Okay. Here's the instrument in our lab. You've already seen it's over the GTC now. Here it is open. The interior, just to give you some idea of what the interior looks like, this is just one quadrant. This is the quadrant of one side of the system that contains, there's the detector assembly. Here you can see the Wollaston prism for doing polarimetry. There's a little flip mirror right here, which allows you, when you're doing spectroscopy, to monitor the field to make sure you're still centered on the slit without actually having to move the grating, which is on this turret right here. So that's a nice little innovation. Let me back up a second here. Of course, there are cold motors throughout the interior. We monitor the temperature. This whole region is at about 10 Kelvin, so it's pretty cold. Okay. The detector is a 320 by 240 Raytheon detector. It's a block impurity band arsenic oak silicon detector. This shows you the quantum efficiency. It's really the quantum yield. This line is in a kind of nonsensical location. There's 10%, 20%, 30%, 40%. So there's 50% QE right in here. It's fairly flat across this region. It's one of the nice virtues of these blocked impurity band detectors. Really quite nice. Below about 10 microns, well, say around 5, the QE drops like a rock. It's not very good. That's why you don't do near-infrared work with this kind of a detector. So, okay. One of the disadvantages, an artifact that you should be aware of, is that with really bright objects, there's crosstalk. And this is an electronic and detector issue that is inherent in the detector. This shows a bright object, Beta Pictoris, really bright. And you can see these little crosstalk spots which follow the row. And there are some other artifacts. You can maybe just begin to see part of it in the vertical direction. So if you want to look for something faint next to something bright, you need to be careful and be aware that these artifacts can be present. And this gives you some idea. They seem to be less than 0.4% of the peak. But there are ways around it. And as long as you know that they're there, then you can work around it a little bit. And we'll talk more about that, too. Okay.
But the crosstalk spots are not always present, right? It's only for very bright objects that we see them.
I suspect the crosstalk spots are always present, but if the object, but once the object is faint enough, then they're probably not going to show up. I mean,
I thought it was if they have to be of a certain threshold before we start to see them.
I think that there is a certain threshold by when you start to see them, but the threshold is probably, has to do with the other noise in the detector and so on. So, that's always been my understanding.
Okay.
Is that not consistent with what you know?
I believe there's a threshold because it's how the array's read out. Once you hit one of the readout circuits too hard, it kind of switches on the crosstalk.
Okay, then I stand corrected. Okay, fine. So there is objects brighter than a certain amount. You should worry about this, I think. Okay, the optical layout is really a very, very simple one. Really simple. We tried to keep it simple. Here's the telescope focus. We have a transfer mirror which produces an image of the telescope pupil here. It reimages this focal plane here. Then you have a conventional spectrograph with a collimator, a camera, and the detector. And that's really all there is to it. The pupil we do baffling around the pupil such that this entire interior region here can only see the outside world through the little hole at the pupil stop. And that's how we can keep this interior background level down very, very low. The system is fairly severely folded, and so that's why the camera is quite small, actually, and fairly compact. The enclosure looks in fact, it's almost exactly the scale shown here. It's nice hexagonal a cross-section, and there's a plate, an optical bench, which is halfway between the top and the bottom, and we have optics and other components which are attached to both sides. Here's the crowd cooler cold head, and then the entrance windows over here, and you can see the beam moving through there. What you actually see, again, this is almost exactly the size of the detector as projected onto the screen. This is the top, and essentially this is a real drawing of the interior. You can see motors here. The optical components are inside of here, and the beam basically enters through here, hits this is the transfer mirror here, a flat. Here's the collimator mirror here. The beam comes over, hits another flat, which drives it through a hole in the optical platform. Then you can see there are field stops and halfway plates and so on here at the entrance in a wheel. We also have filters, spectroscopic slits, and pupil masks at this location right in here. And then once you hit the collimator, you're essentially into the spectrograph subsystem. On the other side, the beam pops through the hole, moves along here. It can go through the Wollaston if it's inserted, and that can be retracted. Can hit a grating, one of 4 gratings on the grating wheel, or a flat mirror for imaging. Comes over, hits the camera mirror, and then onto the detector. So it's a fairly compact system, but the optical design is actually pretty straightforward. And most of the space is taken up by motors and so on, which are used for the various components. Okay, the windows themselves can be changed in real time. We are the well, we didn't come up with the idea, but we're the first people, as far as I know, to implement these kinds of window holders on these major facility instruments. This is what we call a ferrofluidic feed-through. The bottom line is that you can actually change in real time among the entrance windows. The entrance windows that we've got are zinc selenide, potassium bromide, and KRS-5, each of which has its own pluses and minuses. And the only thing that you probably are interested in knowing is when should you use one as compared to the other. And it really depends. The zinc selenide has a very high transmission at 10 microns, but none at 20. So if you want the best, you're only working at 10 microns, then this window should be inserted. Potassium bromide has a little bit lower at 10, but it's also high at 20. So generally, you'd want to use this if you're doing both 10 and 20 micron work. But the only problem with that is it's a water-soluble window. So if it's a high-humidity night, you probably don't want to be using that. Finally, the most robust window is KRS-5, which isn't bothered by anything. But unfortunately, it has a lower transmission at 10 and 20 microns. But if the night isn't all that good from a humidity standpoint, then this may be the window that you want to use. You normally won't have to worry about this. It'll be up to the operators to know what the quality of the night is, and they will be the ones who have to decide this. So, the complement of filters is fairly large. Here are the central wavelengths. You don't have to look at this in too detail, but we try to cover both of the windows fairly well. Let me bring this up instead. Here's the 10 micron window. There are a set of narrowband filters, specialized filters, for example, those which cover certain features such as the argon 3 and the sodium 2 lines, neon 2 lines, sorry. And then there's the broadband filter, which covers the full window. In the 20 micron region, we have a few windows. These are narrowband windows. And I think something came up to show, yeah, the broadband. We have no idea if we'll be able to use the broadband. We're going to find out once we are operational. The broadband filter, you may be so flooded with background at that wavelength on higher water vapor column density nights that you can't read the detector array out. We read it out typically every 15 to 20 milliseconds. And if the background is too high, the wells fill up even before we can read that out. So we don't actually know if we can read it out fast enough under some of those conditions. I'm not going to say much about this. There are 2 panels. For general operators, there are 2 panels that this one allows you to set up and start the integrations, of course. I mean, this is fairly all the standard features that you would expect to configure and observe, stop, start. This is actually, we were in the window imaging mode when we took this. It might even be the pupil imaging mode, I'm not sure, but I think it's the window imaging mode. And but the point of this is you also have a display which shows you can show you the accumulated image as well as the nod position A, nod position B. Oh, I only have 5 minutes left? Oh my gosh, okay. Well, let me rip through this. All right. There are IRAP data reduction scripts that are available. You can get a hold of those. Okay. Let me get into the observing modes really quickly. I don't really have too much to say. I'll just describe them relatively quickly. There's the imaging mode, which is what you might fully expect. Gives you a 26 by 19 arc-second field of view. Your diffraction limited down to 8 microns, Nyquist sampled. This is an image taken with a T-Rex at Gemini south of a supernova remnant. And the key thing about this is it shows you the kinds in 46 minutes. This was one of the best nights I've ever seen. We were getting 100 microjanskis as the 1 sigma noise on this central point in the supernova remnant. That's 1987. That was a really good night. But that was a real observation. Okay. In the case of the spectroscopic mode, we have two what we call low-res gratings and two moderate-res gratings. The resolving powers are roughly 100 or so in the low-res and roughly 1,000 in the high-res mode. The kinds of work that you might want to do in those modes, of course, are to look at the silicate feature, which gives a lot of information about mineralogy, radiative transfer, and so forth. The 20-micron region has a silicate feature. There's been virtually no work done at those wavelengths, so that's virtually untouched territory. Okay. The polarimetric mode is completely unique on this system. We'll be able to look at the O and the E images. In the polarimetric mode, we have half-wave plates. All the components are within the system in cold. We have to have a focal plane mask. There's a Wollaston dual beam analyzer, so you get the separation of the orthogonal components of the polarization onto the detector, and the mask allows you to get an image without the overlapping of those components. And in order to we actually rotate the plane of the polarization by rotating the half-wave plate. Okay. Right now, we can only work in the 8 to 14 micron region, primarily because we only have a half-wave plate for that region. But we believe that there's reason to expect that we'll be able to operate in the 20 micron region as well. I won't say too much about this since I'm getting a bit behind. The mask might look something like this. You can see how the O and the E's are split in the focal plane, and so you have to at the Wollaston, and so in order to prevent overlap of the final images, you actually have to have a mask like this upstream. If you get images at several different angles of the half-wave plate, then of course you can combine those, just as shown here in this now famous set of slides. You can get the polarization, you can get the Stokes parameters, and then the polarization and the polarization angle, and end up hopefully with something that looks like this. This is where you're heading. It's a unique capability that we're really hoping to really do some good stuff. Well, I did have a few things about the science. I'm not going to go into this. I'll just skip across this now, and it's more telling you a little bit about what you can do in polarimetry, and I'm going to skip through these fairly quickly and just move ahead. Yeah. That's a good point. Maybe Chris would like to say something about the instrumental polarization. There's some laboratory, during the commissioning in the lab, we got some information about that. Chris did the lab testing too. Should be, but we'll find out. Oh, sorry. So we also the final mode, just to kind of brief you on, is the coronographic mode. This is, as far as we know, the first mid-infrared coronagraph ever used from the ground. It should help with imaging. It's this initial system, we can upgrade the system as time goes on, but our simulation suggested that this should do just fine. It has a 0.84 arc-second radius top hat mask, and in the telescope focal plane. Same pixel scale as the imaging. It's essentially like the imaging, but with a coronographic spot in the focal plane as well as pupil mask. So we have a rotating cold pupil mask that fits the shape of the pupil, the hexagonal shape of the pupil. We did a lot of simulations. Chris Fotopoulos at Hawaii, who's on our team, did a lot of simulations to help us understand whether this would be a mode that was useful to put in. And we came to the conclusion that it is very useful. These are the kinds of simulations. This is actually, you can see there are some simulations of the sky and so on in the pupil. And let me just move on a little bit quickly. This is kind of the whole stream. So you had, this is a truncated PSF at the beginning. We put a little top hat mask there. There's the actual mask itself. It's a little spot that's been attached to a zinc selenide substrate. And then there's a pupil mask that's a little bit more complicated than this, but you get the basic idea. It's put in at the pupil. And so you end up having the input PSF. Here's the image at the pupil that you use this mask to block, and then you have the output. The most important point are in the numbers. And note that these are logarithmic. And so this would be the input point spread function. When you put the mask in, the simulation suggests to us that there's actually about an order of magnitude beyond, this is the occulting mask within here, of course, so you can't work within 0.84 arcseconds. But outside of that, we think that under good sky conditions, that the PSF should be suppressed by about a factor, an order of magnitude. And what that means is that basically, if you're looking at, say, substellar objects, I'll just show you this, and you're worried about subtracting the point spread function so you can look at substellar objects around a brighter object. If you don't use the coronographic mask, your limit is going to be set by your abilities to subtract from the PSF. And for this kind of star at a certain distance and so on, we did the simulations. Your limit is going to be, this is about a millijansky right here. Whoops, sorry, to back that up. And so what that basically tells you is that for substellar objects that are this age and using various models, this is just to kind of orient you, you can get down to brown dwarf, into the brown dwarf regime right at the boundary of 10 or so Jupiter masses, maybe 10 to 15 Jupiter masses in that vicinity. That'd be a 5 sigma detection. With the coronographic mode in place, you should be down to the essentially the natural background limit, and you should be able to get down to 5, 6, 7 Jupiter masses in terms of detecting the thermal emission. That should be very exciting. We have a nice program led by Rafael Rebolo to do that as part of our CanariCam Science Team observations. One other point about the coronographic spot is you can obviously, when you're looking at a bright object, you can obviously put that in, block the bright object, and that releases you from this problem associated with the crosstalk. That's an engineering use of it. And so if you're in a bright region, you're in a region around a bright object, then you can get rid of it by putting the mask in. Okay. I'm going to end now. Let's go into signal. This was something I think you wanted me to talk more about. But let me just bring up some quick comments about the signal to noise. And this is the last part of the talk. It's relatively straightforward to predict on paper what the signal to noise ratio is going to be for a set of observations. We all know the standard equations, and offline I'd be happy to go over this in detail with anybody. But one of the key points to keep in mind are that the integration time that you need to get a given signal to noise ratio when you're in the background limited regime that we're in goes as 1 over the 4th power of the telescope diameter. So by increasing the telescope by just a factor of 2, the amount of time that it takes is 16 times less with that bigger telescope. So you gain a huge amount. The GTC should be a really remarkable telescope as compared to even 4 or 5 meter telescopes and potentially even Gemini. It should be at least comparable to Gemini. So there's a big gain. So the big telescope helps you a lot. Also, but there's another point to make here, and that is that the limiting flux also is dependent heavily on the emissivity of the system. So the time it takes to get a given signal to noise ratio is also proportional to the emissivity. So you can degrade the effects of having, in terms of sensitivity, a large telescope aperture by having a dirty telescope. So this really puts a big burden on the people at the telescope to keep the telescope clean and to keep it high quality. So just to make it, so if the emissivity increases by a factor of 2, you've taken a 10-meter telescope and reduced it from the standpoint of sensitivity to an 8-meter telescope. So this is not to be ignored. It's extremely important. Okay. Limiting sensitivity numbers. We know that we can couple these into reality through our experience with T-Rex. And the best we've ever seen, I've already mentioned to you, was roughly 100 microjanskis in an hour of observation. If we could actually scale that, and we would find that we would be doing roughly 50 or so microjanskis, 1 sigma in an hour on the GTC. But in fact, the number I'd like you to take away with you is this number right here. So the number to keep in your head is roughly 1 sigma in 1 hour of chopped integration, if you're doing photometry with the broadband filter and even some of the narrow bands, is about 100 microjanskis. That's the number to keep in your head. You can scale that number by using the equations that I had in the previous slide. You can scale that number to come up with the spectroscopy line and continuum sensitivities as well. The coronographic sensitivity is going to be very similar to this, except it's reduced by 60% because of the extra masks that are in there. And finally, the polarimetric sensitivity, the signal-to-noise ratio that you get is related to the accuracy of your polarization by this equation here. And anybody who wants to know the origin of this, it's fairly simple. Needs to talk probably to Jim Hough, but we could talk about it offline. But these are the kinds of numbers. If you have a signal-to-noise ratio in your photometry that's about 360, let's say, on a 50 millijansky source, then you'll end up having a 1 sigma of 0.4% in your polarization. So you basically use this equation to determine what you need here, and that'll tell you what you get in terms of the polarization accuracy. Almost done. Okay. So the number to remember, signal-noise ratio of 1 in 1 hour chopped integration, 100 microjanskis, and then you can use this kind of equation where you've got bandwidth, the signal-noise ratio, and so on to extrapolate. The one caveat then is that in some cases at the higher resolutions will be read noise limited, and so it bottoms out at that point. You can, even simpler thing to do is to go to the signal-noise ratio calculator, which we have. I'll give this information to you so you don't have to copy down the website where our signal-to-noise ratio calculator for CanariCam is. This gives you all the information you need, and you end up, just go through the numbers, and you end up getting the signal-to-noise ratio. Okay. Sorry I ran over, but...
Thank you very much, Charlie. That was very illustrative. Very good talk. Some very quick questions, because we have a limit, and it's that lunch is at 1:30, and we cannot go beyond that, because then the cafeteria gets full.
I have 2 quick questions. Do you have any empty holes in the filter wheels in case somebody want to?
I'm sorry, can you repeat
Do you
that?
have any empty positions in the filter wheels? I mean, any position available if somebody want to buy some filters?
I'm not sure if there are any positions left in the filter wheel or not. I thought everyone was full, but it's possible. Do you know, Chris, whether we have any empty positions? He's going to find out for you.
Well, I will ask you later. Well, the other question is about the...
By the way, the only... there probably are some filters which may prove to be less useful.
Okay.
And in the longer term, it'll be a GTC decision of whether they want to warm the system up and open it up and replace the filters.
Okay.
So if there are specialized filters that are important, I suspect that the GTC will try to accommodate that. As time goes on, we may wish to remove some of these filters.
Well, the other question is related with data reduction. You didn't have much time to talk about that, but I understood that the idea is to use the T-Rex scripts.
Yeah, the Gemini has and maintains the IRAF packages for doing mid-infrared data reduction. So it's been our policy to try to orient people towards that because it's well documented and it's maintained. And
this is based on IRAF.
Yeah, it's based on IRAF. We have at Florida potentially through the CanariCam science team we can try to disseminate IDL routines which have been developed. And so we have IDL packages that we don't support except for ourselves, but certainly it's the kind of thing that we can talk to people about trying to make it available more generally. However, we don't necessarily want to be on the hook for having to support software packages out in the open. But the CanariCam science team may decide, I haven't talked about the science team, but we may decide that it's something that we can, as a team, help people with and support if we're using, if those members on the team who are using IDL. Some people have other packages that I can't really speak to, but the official software is IREF.
Okay, thank you.
Sure.
So can I make two very quick comments? So there's actually no filter positions open.
I thought they were all full. Yeah.
Very quick.
Yeah.
Maybe it's not very quick, but I'll try to make it quick. Okay, over lunch.
Okay.
I think we.
That was easy.
Javier.
Humberto. Here, Humberto. Here, let me get you set up.
But that was very nice, Charlie. Thank you very much.